Professor Reddy doesn't need any
Good evening.
introduction since he is one of the pioneers in the environmental geotechniques and sustainable engineering. He is Professor of Civil and Environmental Engineering, the Director of Sustainable Engineering Research Laboratory, and also the Director of the Geotechnical and Geoenvironmental Engineering Laboratory in the Department of Civil and Materials Engineering at the University of Illinois at Chicago. He has over 25 years of research, teaching, and consulting experience within the broad fields of civil, geotechnical, materials, and environmental engineering, addressing the topic among sustainability, resiliency, infrastructure, water, energy, and the environment in urban setting. His research includes laboratory studies, field experiments, and computer modeling, ultimately leading to fundamental advances and practical solution to the real world problems. Dr. Reddy is the author of 3 books pertaining to geoenvironmental engineering, electrochemical remediation technology, and sustainable remediation of contaminated site. He is also author of 193 journal, 14 edited books and conference proceeding, 12 book chapters, and 175 full conference papers. He has served or currently serves as an associated editor and of editorial members of over 10 different journals. He has also served of various professional committees, including of Geoenvironmental Engineering Committee, Technical Coordinate Council of Geo Institute, American Society of Civil Engineering, and etc. Dr. Reddy has received several awards for excellence in research and teaching, including the UIC Distinguished Research Award, the University of Illinois Scholar Award, and the UIC Award for Excellence in Teaching. With this introduction, I welcome Professor Krishna R. Reddy for the lecture.
Okay. All right. First of all, I want to thank Professor Sarath Das for inviting me to be part of this lecture series. It's a very interesting lecture series. So I wanted to present something that was done recently in my lab on something related to fly ash. So I readily agreed to give this presentation. What we are looking at is fly ash amended with bentonite and can be used as a liner material in waste containment systems. And is it sustainable? So based on the life cycle assessment, we try to answer that question of sustainability. So before I get started, I want to thank the real people who did this work. First one is the Dr. Ravi Teja, assistant professor at SRM University, Amaravati, AP, India. He visited my lab under DST Sire Fellow during August 2022 to early this month. So he just returned back to India. So he was working for the last 6 months in my lab on this project. So all the work that I'm showing you is under his leadership. And the person that you see in the picture next to him is my PhD student, Jagdish Janga. He was helping him. His research is on a different topic, but he was helping. 1 second, okay? 1 second, please. 1 second. So, okay, sorry. All right, so this is my PhD student helping Ravi Teja. And I had another visiting student from India. Everybody at Dhanbad should know him, Anshumali Mishra. He's a PhD student at IIT Dhanbad. He was recently a Spark Fellow at UIC. Again, he spent almost 5 months in my lab. He helped on sustainability assessment that I'm going to show you. And then funding for all this work was from SERB, and UIC. So in the presentation, what I'm going to do is tell you a little bit about why we took up this project. Of course, there's a problem of fly ash everywhere, including India. And also, we are designing waste containment systems with liners for different types of waste, solid waste and liquid waste. They need liners, and we have shortage of materials as the liner materials. The question is, can we use some of fly ash as a material in the liner systems? So based on that premise, we set our research objectives. I will mention those things. And then first thing what we had to do was look at fly ash. Fly ash itself is not suitable. So we were looking at amending with bentonite. So we characterized first fly ash and bentonite that we used in our studies. And then we basically did physical, chemical, and geotechnical characterization. Then we tried to test what is the optimum amount of bentonite that we need to add to make fly ash as a suitable liner material. That is done based on the compaction test, hydraulic conductivity test, shear strength test, and interface shear strength test. Then, of course, ultimately this liner system has to contain the contaminants, right? So we try to look at, typical contaminant we looked at is phosphate. So let's say if you have a phosphate leaching from the waste, or if the liquid waste has phosphate, can this liner system remove that or through sorption mechanisms? And if the liner is contaminated, will that affect any way the mechanical response? What we looked at is the compressibility. If it is contaminated or if it is exposed to phosphate, will the compressibility of the liner system vary? Then, if all that looks good, then is it a sustainable option as compared to the other liners options that we have? And that is done based on the environmental, economic, and social aspects, often known as triple bottom line. Then I will have a concluding remark. So this is my agenda. And as I said, this is all the work that is done by Dr. Ravi Teja in last 6 months. So the problem with fly ash is we're talking about coal-fired power plants, many of them in India, providing the power. And obviously, all these plants will generate the fly ash. And, we know very well fly ash could be a problem. And there could be, the damage of ash ponds and unintended exposure of the fly ash to people. And, a lot of times we are just disposing of those by the power plants, sometimes without liner systems. So India is the second largest fly ash producer, I understand, the 226 metric tons per MT per year. 38 MT per year is disposed of in ash ponds. Ash ponds occupy 65,000 acres of valuable land area in India. And of course, it's causing some environmental concerns, as well as making the land used by ash ponds unproductive for any use. So to avoid all these problems, can we beneficially use fly ash? So that's desirable option. If you look at statistics on the fly ash use currently, so this shows this bar chart shows the generation, and then this line diagram shows utilization. For example, fiscal year 2020, you see here, so over 220, MT, generation. And if you look at this line, about 85% of them are being utilized, which is not bad. It's extremely good to utilize 85%. But that is, due to these different uses. So this is the data taken for the 2021-2022 first half of the year, how that fly ash is being reused. As you see here, there are a lot of uses, but about 18% is unutilized. So we are looking at using that one as a liner material. But in addition to that, the newly generated fly ash is being used, but we have large amounts of fly ash that is already existing in ash ponds that need beneficial reuse. So that, there's a lot of these materials that are available in pond ashes, ash ponds. So can we use that one for beneficial purpose? So I see a lot of landfills are being constructed in India, and most of them follow US regulations, liner systems that consist of low permeable soil liner. And on the top of it, you have a HDPE geomembrane. That's a composite liner. So this soil liner has to have a permeability less than 10 to the power of minus 7 centimeter per second. So the problem is at many sites, you don't have a soil, even if it is compacted, you don't get into power minus 7 centimeter per second. I have personal experience when I was at IIT Madras last summer. I visited a lot of landfills. So the most complaint that they have is they don't have a suitable soil to use as a liner at the site. So they were importing from long distances, and that has been a big problem. So, but the fly ash is available close by. Is there a way that we could use as a alternative to compacted clay liner? And of course, you have impoundments or ponds that are being lined, and they also have a composite liner. So you have a compacted clay liner at the bottom. You have a HDPE geomembrane on the top of it. Again, the problem is this compacted soil has to have a permeability less than 10 to the power of minus 7 centimeter per second. So at the site of these ponds or impoundments, you don't have a soil. Even if you compact it, you will not get 10 to the power of minus 7 centimeter per second. So what are the alternatives? Do you want to import from a large distance? And that is also becoming extremely difficult. They are not able to find anything at a reasonable distances. So what is the alternative? Can we use fly ash as an alternative material for compacted soil? So the liners are very important part of the containment systems because they minimize the seepage and also contaminant transport into the subsurface. So this is extremely important in terms of the environmental protection. And as I mentioned, compacted clays are commonly used. Instead of compacted clays, you can use the geosynthetic clay liners. These are basically geotextiles, bentonite sandwiched between geotextiles. And I understand that these are not available easily in India. They have to export from some other places, or even those we have in India, they are not high quality, as I understand. So they have to meet 10 to the power minus 7 centimeter per second. As I said, scarcity and increased cost of low permeable clays, and as well as GCLs at near the project sites are challenging tasks that are being faced in India. So are there any possible alternate liner materials? So that's when this fly ash, can we use the fly ash as a liner material? The benefits of using fly ash as a liner materials are, so it has a relatively high cation exchange capacity compared to the typical site soils, high contaminant absorption capacity, and you are using the industrial byproduct. So you are beneficiating the waste, or we don't want to call the waste, it's industrial byproducts. And then they are available close to the project site. So you don't have issues about long distance transport of the materials. The main challenge of using fly ash is that hydraulic conductivity is more than 10 to the power of minus 7 centimeter per second. That means it cannot be used as a liner material because it does not meet the regulatory requirement of low permeability. So what can we do? Can fly ash be amended with bentonite to overcome this challenge? If so, how will it perform as a liner material? So that is the basic question of this research. So based on that, we set a research objectives. First thing is we had to select the bentonite and fly ash, and we characterize those for physical, chemical, geotechnical properties. Then compaction, and the hydraulic conductivity. So as I said, whenever you are using a material for a liner, the first thing that you have to do is see if it meets the hydraulic conductivity of 10 to the power minus 7 or less. So as fly ash alone is not going to meet the requirement. So if I have to add bentonite, what is the optimum bentonite content? So that is the question based on the compaction and hydraulic conductivity. So if we can find out that optimum bentonite content, then is that material has enough shear strength? And do you have interface shear strength? Because soil and geomembrane is used always as a composite. Especially, you have the liner on the slopes also. Will that be stable or not? Okay, that's the question that we need to answer. And after that, is it effective chemical containment or not? Can it contain the chemical or pollutants in an effective manner or not? So that's investigating. We use the phosphate as a typical contaminant, and we try to see if it can be removed by the bentonite amended fly ash. And then again, we wanted to look at from mechanical point of view, if a liner is exposed to the phosphate, will it change the compressibility? And then, is this option sustainable? So these days, everything that you are looking at it should be, look through the lens of sustainability. You don't want to do anything if it is not sustainable. So we'll evaluate the sustainability of what we are proposing. The materials, since this work was done in US, bentonite, we got a bentonite that is typical in the US. And we got the fly ash, class F fly ash. And again, we got it from a source in US. And we had Indian fly ash that's obtained from Vijayawada Thermal Power Station. Of course, you cannot easily, bring it to US. So we had independent testing done in India at SRM University by Dr. Ravi Teja's students. So here is there's a lot of effort went into getting these properties. So, but we characterized for specific gravity, grain size distribution, Atterberg limits, and compaction, and then free swell, saturated hydraulic conductivity, and some chemical characteristics, pH, ORP, and electrical conductivity. The main thing out of all these things is the hydraulic conductivity if you are evaluating the liner systems. So of course, the bentonite would have a low permeability, less than 10 to the power minus 7 easily. But fly ash does not have a 10 to the power minus 7 centimeter per second. So here is the particle size distribution. So bentonite, of course, is a very finer, mostly clay fraction. The fly ash has mostly silt fraction. Then other important thing that we should look at it, whenever you say industrial byproducts, one question comes up is it safe? Maybe it's contaminated. It may, pollute the ground, right? That's the first question. For any waste material, when you are using it, the common concern is, will it have any environmental problem? Will it pose any environmental problem by just using that one? Maybe leaching of the contaminants. So for that, to evaluate that one, you need to do the total concentrations. How much total concentration of these contaminants we have? You expect mostly metals in the fly ash. So we analyzed all the metals that are recommended by US EPA. So the total concentration. So total does not mean anything. So you have to look at what is leachable out of the total concentration. So SPLP is synthetic precipitation leaching procedure. This kind of simulates the rainfall. If it rain falls on the fly ash, and if you collect the liquid that is passing through it, what are the chemicals that you can find it? So that's a SPLP. This is more realistic to the field scenarios. The TCLP is toxicity characteristic leaching procedure. This is the method that is developed by US EPA. And you have to do this leaching test and find out the concentrations. And then US EPA has the regulatory limits. So you see the concentrations for some of the metals. So you compare your TCLP concentrations with these allowable concentrations. And if the concentrations of your TCLP concentrations are less than this, then that material is considered non-hazardous. So this is how a material is designated as hazardous or non-hazardous. That has huge implications. If the material is characterized as hazardous, then you cannot use for typical applications, and it has to be sent to a hazardous waste landfill. If it is non-hazardous, then you can use it as a construction material. So just a comparison of the results that we got for the fly ash, and compared to TCLP concentrations, they are way low, right? So you see 0.17, this is 5 milligrams per liter arsenic. So that's, all of them are extremely low. That means that fly ash is non-hazardous, and you don't have potential for leaching of toxic metals from this fly ash. So it can be used as a good material, construction material, and it can be used for liners also. So no toxic metals were found to leach out of the fly ash in considerable quantities. There are some toxic metals detected in the leachate, as you saw. There are some numbers, but they are very low and definitely less than regulatory threshold. For example, arsenic is 55 milligrams per kilogram total, but TCLP is 0.17. The regulatory limit is 5 milligrams per liter. So that's not a problem. But we need to keep in mind, this is done on fly ash that we got into the lab. If you are working on fly ash, it's better to test your own fly ash. So fly ash can vary from place to place. So we recommend that you do the leachability test before you evaluate for other properties. Okay, so now we don't have any problem with the fly ash. So we try to look at the, okay, what should we do? Hydraulic conductivity is more than 10 to the power minus 7. So we need to add bentonite. How much is the bentonite? So we did compaction tests on the fly ash itself, and then adding bentonite in the percentages of 5%, 10%, 15, 20, 25, 30, 35, 40, 45, and 50%. Okay, so these are the compaction test results. So the main thing, if you can take maximum dry density and optimum moisture content from those compaction curves, this is how it looks. See the bentonite content on x-axis and optimum moisture content on y-axis here. And also second y-axis is maximum dry density. So this is the maximum dry density. You see it increases and then it slightly decreases. Optimum moisture content, decreases and then it starts increasing. We found out that around 20%, that maximum density is attained. And that's kind of optimal from compaction point of view. And then we looked at, so this is kind of information why, at 20%, we got the maximum dry density. There's some explanation for some SEM images. We are still looking at explaining the fundamental reason why that observed behavior is seen. So you have a compaction. Then we need to do the hydraulic conductivity test. And when you are evaluating the liner systems in the US, we don't accept any rigid wall permeameter tests. So those are not accepted. So you need to do this triaxial flexible wall permeameter according to ASTM D5084. Otherwise, it won't be accepted. So we did these tests at UIC. You can see, we have multiple cells like this, and then we can run multiple samples. I think we can do 5 or 6 at a time. So we prepared the samples, and then we follow this ASTM D5084 and determine the hydraulic conductivity. So, for different compaction, for example, this is the bentonite. This is the compaction curve, and you can find out the optimum moisture content and dry density. But we are more interested in the hydraulic conductivity. You can see the hydraulic conductivity, it is very low, no matter, at what moisture contents that you compact, the densities that you compact. It's expected because of the bentonite. But we are not interested in just the bentonite itself. We are interested in fly ash. And then we want to add that bentonite that has low permeability to the fly ash that has high permeability to make the composite has a low permeability. So as you see, when you have a 0%, permeability is very high. As we add bentonite content, as you see, the permeability keep decreasing. And you can see the 10 to the power minus 7 is the regulatory limit. So around 20%, you will see that it meeting the requirement. So we did the test, the small column and large column, and we found out that, at the 20%, you can meet the requirement of 10 to the power minus 7 centimeter per second. Okay, so that is our optimal mix. So 20% bentonite, if you add it to the fly ash, we're going to get the minimum required hydraulic conductivity. Then, this liner has to be, constructed on the slope. So you need to have enough shear strength, right? So we did this unconfined compressive strength that can give you undrained shear strength. And as you see, as the bentonite content increases, shear strength increases. After that, it decreases. So this up to 20%, it keeps increasing. And then after that, it decreases. So the other important thing is the interface shear strength. Remember, on the slopes, you have a bentonite amended liner. And then on the top of it is going to have a geomembrane. So you need to see the interface shear because that's extremely important. Slope stability is extremely important. So this is the large scale direct shear device that is available at SRM University. Dr. Raviteja's students did these experiments. So this is extremely important. As I mentioned, you have a bottom liner here. This is a side liner. So basically you have a bentonite amended fly ash, if you recommend that as instead of compacted clay. On the top, you have a geomembrane. And then the interface between this bentonite amended fly ash and the geomembrane is the most critical surface in terms of the slope stability. So this, we need to know the interface shear strength between the bentonite amended fly ash and the geomembrane. There are a lot of failures that have been reported due to insufficient friction between these two materials, so liner material and the geomembrane. So we wanted to investigate the interface shear strength properties. So based on that interface shear, direct shear, large scale direct shear testing. So these are all the interface strengths between the bentonite amended fly ash and the HDPE geomembrane. So only one particular HDPE geomembrane was used. That was a textured HDPE geomembrane. And then you look at all these friction angles. So you can see the friction angles vary. Friction angle and adhesion are shown here. Basically, the slope and the intercept. Intercept is going to be adhesion, and then slope is the interface friction angle. And we plotted that one here. And here 20%, it's not bad. You have a higher friction, so that should be suffice for slope stability. So out of all the percentages, of course, if you have less bentonite, friction angle is going to be high. As the bentonite content increases, friction angle goes to decreasing. But at 20%, that seems to be pretty optimal conditions for interface resistance. So based on all those things, that 20% bentonite amendment to the fly ash seems to provide the lowest hydraulic conductivity that we want. It has a good shear strength and it has good interface strength. So we are in a situation to recommend that as the liner material. But remember, we are using this one to contain the contaminants, right? So you need to also evaluate how effective this liner material is for containment of the pollutants. So we used phosphate as a surrogate contaminant, and we basically created this different materials, the liner materials, and then you have a phosphate solution. We did batch experiments. So you mix them, and then you separate them, and then you analyze for phosphate. So you add it to the material, and then you shake it, and then collect the liquid supernatant, and then you analyze it. So how much is, initially, how much phosphate you put it in there, and how much is sorbed onto the material, how much is remaining the solution. So the idea is you want to have more phosphate sorbed to the material, so in order to have effective containment. So these are the results for this fly ash and bentonite if you test individually. So this is initial concentration of phosphate solution. If you put 0.5 milligrams per liter solution, 100% is removed by the fly ash, and then only 40% is removed by the bentonite. So you can see consistently, fly ash did an excellent job, right? So remember, phosphate is an anionic species. So, having a lot of negative charge is not like a bentonite. Typically, if you have a cationic contaminant, you probably see other way around, with bentonite having more removal efficiency compared to the fly ash. But anionic species, so this fly ash seems to be really doing good job. So you test at different concentrations, and then you calculate the equilibrium concentration and sorbed phosphate, and you plot the graphs like this one for fly ash, one for bentonite. So you see the nonlinear response. So eventually it will reach its sorption capacity. So we are basically looking at what is the maximum sorption capacity. And this is definitely model using isotherms. Basically, since we have observed nonlinear, Freundlich isotherm and Langmuir isotherms are the two common isotherms that are used. And then if you fit to the data, we got these parameters, Freundlich parameters, K and N, and Langmuir parameters, alpha and beta. But based on the R squares, you look at it. So Freundlich isotherm is the best fit model for representing the phosphate absorption onto fly ash or bentonite, or calculated 80 to 20 mix bentonite amended fly ash. So the batch experiments gives you, the idealistic conditions, the maximum absorption, but in reality, you have a compacted clay, compacted bentonite amended fly ash, and then the solution is on the top. So the solution has to percolate. So that can be represented by the column experiments, not by batch experiments. In the batch experiments, you are adding it and mixing it, but that gives you the ideal sense. And if you can find that one, if it gives you the high absorption capacity, then you want to do the column test to know what would be the realistic absorption capacity. So here, this is the testing again done in my lab at UIC. So you prepare the sample, and you flush the phosphate solution from top or bottom, and then you collect the effluent that is coming out. So with this one, you can find out how much of the phosphate is retained, how much phosphate is coming out. Here are the results. So first, what we did is we prepared the sample and we used the distilled water as the permeant. And if you use the distilled water as a permeant, we are looking at that 20% bentonite, 80% fly ash mix, the sample, right? So you see the permeability is very low. Now we changed into the phosphate solution. So a lot of times this, for chemical compatibility assessment, this is what typically done. So you use the water first, and then you flush with the contamination solution of your interest. And then depending upon the chemistry that happens between the permeant and the liner material, sometimes hydraulic conductivity could increase or decrease. This happens quite a bit in bentonite-based liner materials. But based on this testing, you see that it does not change at all, which means it's really good. This chemical compatibility is really, really good. So there's no effect on hydraulic conductivity. And we get very low pore volume, low outflow. So we are collecting every 0.25 pore volumes and to analyze the phosphate concentrations. And the phosphate retention is higher due to high cation exchange capacity, and seems to confirm the batch test results with this one. Then, as I said, the phosphate is going into the liner material, and it is retaining there. So the question is, will that affect any mechanical response of the liner, right? So because you're putting the liner, and then you have based on the top of it is basically you're applying the load. So what happens to the compressibility? Just so we use that as a indicator of the mechanical response. So we tested. We have all these consolidometers. So we created all these fly ash bentonite amended fly ash, again 20 and 80%. We had in one test we had only water, and in one test we had bentonite only water, fly ash and only water, and then we had bentonite amended fly ash only with water, and then we tested one with low concentration of the phosphate, and one we tested with high concentration of the phosphate. So based on these results, so you can see the consolidation curves. This first one is for bentonite, the second one is for fly ash, and these three curves that you see here for that bentonite amended fly ash exposed to water versus exposed to low concentration of phosphate and high concentration of phosphate. So see, these three are very similar. So that means the chemistry is not affecting the compressibility. So phosphate exposure or phosphate interaction with the liner material is not really changing the compressibility response of the material, which is really a good sign. So you can see from the CC values and CR values, so compressibility parameters are not affected by the phosphate exposure. And then, we took the SEM images, and we are still in the process of understanding what is going on in terms of the interaction between the bentonite and the fly ash that is making the low permeability and giving us all this favorable response in terms of the strength and chemical containment. So the outcome of this research is 80% fly ash and 20% bentonite compacted at its optimum moisture content can be effective low permeability liner with adequate shear strength and interface strength. And based on the phosphate testing, we show that it is effective contaminant containment material. And phosphate exposure does not affect the compressibility of the liner. Of course, one can argue that, hey, your testing is limited to particular fly ash that you have and particular bentonite that you have. So if you have a different fly ash and different bentonite, you need to look at, how those will perform. So you need to get the samples of the materials that you are going to use and then test them. So different compositional environment, compositional conditions could give you different results. The other thing is, one may argue, okay, why did you use the phosphate? Why not in the real world, you're going to have a leachate that has different types of contaminants. Or if you are using impoundment, you are using the liquid waste that will have a lot of different types of contaminants. So how do you assess those things? So basically, you need to collect the actual leachate, actual liquid waste, and then run the same column test that I showed you with phosphate. You run it for a long period of time. So chemical compatibility tests can go on for years, 1 year or 2 years. So the chemistry that happens in the soil will take some time. So you should see some experiments that are done. We published some papers for, barrier study of all backfill materials. So you can see some papers where, the hydraulic conductivity, other things will change due to the chemical exposure. Then, of course, the lab testing is not enough. So ideally, if it is possible, field demonstration is important. Now, the question is, how sustainable is this bentonite amended fly ash compared to the other liners? So that's where we had to do the sustainability assessment. And we used the triple bottom line framework, looking at the environmental, economic, and social aspects. And what we did is we compare the proposed with other alternatives. The first option is kind of a more default. This is like a standard. You have a compacted clay. Minimum is 2 feet. That's required by US EPA. And you have HDPE liner on the top of it. So this is kind of a most commonly used liner system. So where you don't have a compacted clay, people use the GCL, commercial GCL. So you have a GCL and HDPE geomembrane. That's also very commonly used. But if you don't have those compacted clay, good compacted clay, if you don't have a GCL, like the situation in India, why don't we use the native soil? And then a lot of times you think about, okay, amending with cement and lime. You can amend with cement and lime, you can get the low permeability and other things. So that could be an option. But what we are suggesting is this one, fly ash and 20% bentonite. So this is the option. So compared to these other three options, how sustainable is this, the option that we are proposing, fly ash and bentonite, right? 80 to 20%. How sustainable it is compared to the are there three options that are actually practical to use also, right? So this is the work that has been done by Anshumali Mishra. We presented this at a conference recently, and there's a paper that is coming up on this one. So you can get more details on this one. Okay. So the project for the sustainability assessment, we consider a landfill at a location called DeKalb, Illinois. Sustainability assessments have to be done for specific situations because every specific situation is different in terms of the transport distance of the materials and other things. So we want to have there is a landfill there. Let's say there's a new cell, you want to construct the liner. If we use our option, or if you use all the four options, how is the sustainability? So the functional unit is 1 acre area of landfill or liner. So you can basically the impacts that you calculate for 1 acre, if you have whatever the number of acres you have, you can multiply that one. So the functional unit is 1 acre in comparison. First thing is environmental sustainability. So that is often done by life cycle assessment, LCA. This is kind of a well-established methodology. I highly recommend you to look at the book Sustainable Engineering to get an idea about life cycle assessment. So this is often done by ISO 14040 methodology. So that includes the inventory analysis, impact assessment, and then interpretation of the results. So here is the LCA inventory. Basically, what are the materials that you need? What are the transportation distances? All those things have to be summarized for each of those 4 liner options. And then you can do the impact assessment by using different methods. The Eco Indicator 99 is the method that is commonly used in Europe. And it gives you the environment impacts lumped into human health, ecosystem, and resources. And that gives you overall indicator of those impacts. The other one is the Tracy. This is the method that's based on the data from North America. This is what we use in USA and Canada. So again, this calculates the different indicators of environmental issues, as you see here, impact categories that you have. So this is developed by US EPA. So applying that inventory, applying these impact assessment methods. So for example, if you look at the eco indicator, as you see here on the y-axis, here are the environmental indicators. And they are shown as a normalized, whatever is the highest is 100%. As compared to that one, what are the other numbers? So for example, ozone depletion, the highest is, you see, GMCCL and GMGCL. And GM, this is the lime and cement that I mentioned. And this is what we are proposing. So you see for ozone depletion, the highest impact is from that lime and cement that we're using. And the second worst is GMGCL. GMGCL. And this one is the GMCCL. But if you look at the proposed one, it has the lowest impact compared to the other ones. Even carbon footprint, for example, global warming is the carbon footprint. You can see highest carbon footprint for GMGCL. And then next is this, GM and that lime cement mixture. And then third one is this. And then fourth one is the proposed one. So you can see all the smog, acidification, eutrophication, carcinogens, non-carcinogens, respiratory effects, ecotoxicity, fossil fuel depletion. Look at each of those environmental indicators. You see consistently the geomembrane and bentonite amended fly ash comes out to be having the lowest impacts. By the way, we are assuming that fly ash is available close to the site. That's the advantage you will have compared to the other materials. If you are transporting from large distances, so you're not going to have that benefits of minimizing the transport distances, right? So that's the results. And then you can lump them into these 3 categories of environmental indicators: human health, ecosystem quality, and resources. You can see individually those, and then adding them up, you can see the geomembrane with the bentonite amended fly ash has the lowest impact. That means clearly quantitatively, you can see that sustainability, is this whatever we are proposing that is highly sustainable. So again, we looked at that's the European data, but you look at the Tracy based on the North American data. Of course, these indicators are going to be different depending upon which impact method you're using. And then again, you can see consistently, you find the same results. So the bentonite amended fly ash has the lowest impacts, environmental impacts. And then economics, right? Okay, what about the cost? So we looked at all the materials and including the transport costs, and then we calculated what would be the total cost per liner to place on 1 acre of landfill area. So these are the estimated costs. So GMCCL, that's a geomembrane compacted clay, geomembrane GCL, geomembrane with lime and cement, and there's the bentonite amended fly ash. So it is not the cheapest. Cheapest could be GMGCL. Again, it depends, right? In the US, we have geomembrane GCLs available easily, so it's okay. But if you compare the costs of these materials in Indian context, this will be very high. But we are referring to using these in a situation in US, right? But still, this is much cheaper than these other options. So that's the important thing to keep in mind. So that's the social, no, that's the economic. And the triple bottom line, you have environmental, economic, and social. Social is the third one. So how would it affect the society by this using the different liner systems? So this is the very tough task of sustainability assessment. The social sustainability is always very subjective. So we generally use the rating systems, and there is no universally accepted rating system. So in this case, we use the score of 0 or 1. We identified what are the social indicators, and then we give a score of 0 or 1. 0 means no effect. 1 means there is some negative impact. So lesser score means more socially beneficial or more socially sustainable, socially responsible practice. Again, as I said, these indicators will change. Stakeholders group will change depending upon project. So here we use these as stakeholders. These are the impact categories, and these are the 4 liner options that we have, and we kind of give the rating for this one. Again, this is the hard part of coming with the rating. So most of the times we do the surveys and then average the scores and put them in there. So the lowest one is the best, right? So as you see, GMGCL liner system comes out to be the best socially. And then it comes the proposed one, and then is the lime and cement, and then GMCCL liner. So the socially, people think that you're using the GCL and GM is the better protection compared to what we are doing, but that's always very subjective. Now, how can we combine all the environmental indicators and economic indicators and social indicators into sustainability index? We use the multi-criteria decision analysis. So we developed a framework called Qualix. So this paper that I'm showing that gives you the details about how we do that. And because as I said, economically one option is better, socially one option is better, in the environmental aspects, something is better. So it's like you have all these different contrasting indicators. How do you make a decision out of that, right? So this kind of a framework will help you to come up with a conclusion with the contradicting indicator values. So applying this framework, you can see the sustainability index. Higher the sustainability index is the better is a better option. So CCL is the low one, but the highest one is GCL. But the proposed one is not that far from there. It's slightly less than that, but second best overall. And GMSAA is coming out to be the lowest option. So this is not definitely sustainable. And this is the second option. This would be the third option. This would, in terms of a reverse, this would be the first option, second option, third option, and fourth option. So this is the sustainability index calculated. Overall sustainability index considers here social, environmental, and economic. All of them are considered equal, right? So, but what is your preference? So in this case, these are the same results here. We use the 50% weightage for environmental and 25% for social, and so 25% for economic. Because how do you give the preference, right? So if you are basically, after all, liner is for environmental protection. So you want to give the higher weightage for the liner performance, right? So 50%, that's one. So if you apply that factors, definitely you see that proposed bentonite amended fly ash liner is the number one in terms of the sustainability. So it's better than GMGCL. And then, of course, these two are still lower. So overall, you can make a conclusion that even quantitatively, if you do the typical assessment for a typical landfill, sustainability assessment for a typical landfill scenario, so this proposed bentonite amended fly ash is coming to be sustainable, which is good news, right? So overall, so concluding remarks, bentonite amended fly ash liner can be technically sound and sustainable option for a liner system. And optimum mix is 80% and 20%. So fly ash is found to be effective for the removal of phosphate, and phosphate contaminated environment did not affect the hydraulic conductivity or compressibility. Out of the 4 alternate liner systems evaluated, bentonite amended fly ash liner is the most sustainable option, on par with GCL. And therefore, use of bentonite amended fly ash as a liner material is recommended. So it can be a significant step towards using the fly ash that is available in existing ash ponds as an effective liner material, ultimately protecting our environment. So that's the end of my presentation, but I want to take this opportunity to advertise this in the international webinar series that we have every week on Thursdays. It's in India at around 7:30 p.m. So on different topics. And go to this website. You will find the information about upcoming webinars, registration, and then all the recorded webinars. So take a picture of this slide and go to that website. You will find information on all interesting presentations in the past. Also, another advertisement. I am here. I'm visiting IIT Indore as a Vajra faculty. And we are organizing a 5-day workshop on sustainable geo-environmental practices, hazard mitigation, and environmental protection. So this is going to be in the evenings, 4:30 p.m. to 7:30 p.m. So it should not disturb your day schedule. And it's online. You can watch from your bedroom and register in advance. So I hope to see you all from next Monday through Friday. So with that one, I want to give you my contact information. Feel free to contact me anytime. And these are my lab websites. Please, visit those lab websites. You will find all kinds of information. Some of that could be useful for you. So with that one, I don't know if I took a long time, but with that one, I want to end my presentation. I want to thank again Professor Sarat Das for his organization of this webinar series. And also I want to thank Professor Sumi Siddiqui. I need to meet her from University of British Columbia. She's a very active researcher. So I'm glad to see the partnership between IIT Dhanbad and Dr. Sumi Siddiqui. Thank you so much.
Thank you, sir. So, sir, can you make your video on? Yes, thank you, sir. Yeah, so now, yes, Professor Dr. Sumi Siddiqui is there already. So since early morning, she has joined.
Thank you. This is very, I've been waiting to meet you, Professor Reddy, and this is a great opportunity to meet you. I'm humbled that you have, talked about me, but, pleasure is mine for sure. Thank you.
Yeah, very sure we're going to meet sometime soon. Yeah. You should come to Chicago.
Yes.
Yes. Yes, sir. There are some queries, but some queries have already been clarified by Dr. Robbie Teja
Mhm.
in the chat box. So like there was a question about using class F fly ash or class C fly ash. Dr. Robbie Teja already said that it is a class F fly ash. Then regarding the type of bentonite, it is also sodium bentonite. He has clarified. So there is one more query from Satyajit Portal, whether GCL can replace CCL completely in the liner system, or it can reduce the required thickness of CCL only. Hello.
So in theory, yeah. So can you hear me?
Yes, now.
So yeah, just in theory, yeah, the CCL and GCL are considered to be equivalent because GCL has a very low hydraulic conductivity, but the problem is it has a very thin compared to the compacted clay, and there are a lot of chemical compatibility issues with the GCLs. So a lot of places they don't allow use of GCLs in the bottom liner system. So I mean, in terms of the hydraulic equivalence, you can do the hydraulic equivalence calculations. They come out to be equal. Maybe 2 feet of compacted clay is equal to the GCL, but the problem is that it is very thin. The displacement of the bentonite could be a problem. Hydration of the bentonite could be a problem. So a lot of places, in the state of Illinois and some other states, they don't allow use of GCLs in the bottom liner, but it can be used in the cover systems, because the cover systems, you don't have any issues of chemical compatibility and other things. So it depends upon the situation, and yeah, you need to be extremely careful to use GCLs in the bottom liners, because if some issue is there is no way to fix it. In the final cover, of course you can go back and fix it, but if you put it in the bottom liner, there's no way you're going to go back and fix it.
Yes, sir. Next is another from Kunal Thakur. If the TCLP constants limit is greater than USP at TCLP, then soil contaminant will occur. Then what is the method can we use for remove it? I mean, to remove it. Mr. Kunal Thakur, are you there?
Yeah, I mean, if your material, is showing the TCLP concentrations more than allowable levels, so that basically becomes hazardous. So you need to stabilize it. You need to some way to modify it so that the TCLP concentrations are lower. So once you stabilize it, then it becomes a non-hazardous. So that's what happens if you have a hazardous waste. If the material is hazardous and you have to send it to a hazardous waste landfill, you have to spend a lot of money. So instead of that, you stabilize it and make it non-hazardous and send it to a non-hazardous landfill. You save a lot of money. So same way here, you can do that, but then you have to evaluate the stability of that stabilization under the exposure of the leachate conditions. So you probably have to check it, So yeah, don't give up. We are engineers, so we can make it anything to work. There are ways to handle every difficult situation that we face.
Yes, sir. So another is from Pintu Kumar Saw. Why do we generally use TCLP if SPLP is more realistic?
So as I said, TCLP is recommended by US EPA to characterize if the material is hazardous or non-hazardous. So from leaching point of view, in a realistic field scenario, leaching point of view, SPLP is the best option. That simulates I mean, again, SPLP is like a precipitation of the rainwater, right? Precipitation or infiltration of the precipitation. So that's what you are looking at it. But in case of liner systems, it's not rainwater even. It is a contaminated solution or leachate. So that's what you need to leach it through. That's why column experiments using the permeant that is representative of the leachate is extremely important. But if you are using the final cover or any other engineering applications, if you are using the waste materials in embankment or roadways, So if you are trying to analyze it, then SPLP would be the best option.
So the final question, okay, so one more question. Kamran Ilahi. So thank you for Professor. Please throw some light on how rise in pressure of leachate induced by chemical reaction can cause the liner system to shift or deform, leading to cracks and fissures in the landfill. Our rise in pressure, okay.
So I think that the pressure needs to be accounted. So whatever is the pressure, you have a liner, you have a lot of waste on the top of it, and you have a pressurized situation. So under those conditions, you have to see, you can simulate the pressure in triaxial cell, and you can do that. But you will not have much problems in the bottom liner system because it's always wet, and you probably have more compaction. Whereas when you look at other scenarios, where conditions could vary quite a bit, especially in the final covers, it could be shrinkage, swelling, cracking that could happen. But in the bottom liner, those issues would not be that significant. So you have to reimagine what could happen in the field under the your expected project scenario, and consider those aspects. But shrinkage, swelling, wetting, drying, those are all the problems that you face in the final cover on the top, because that's exposed to the atmosphere. But the bottom liner is mostly stable from in terms of the outside environmental conditions. But you have under pressure, again, the compressibility is important. You want to look at it, and everything is confined at the bottom, so it could compact uniformly. And what will happen to that with generally the pressure should it, and then hydraulic conductivity and the strength and all those things should go should be better. But you can test that. You can apply the pressure, and you can model the testing to represent the field scenario.
Yes, sir. The last question is that does Class C fly ash won't be effective compared to Class F? I think Dr. Ravikant has also explained that they have used Class F. Anyway, sir, so if you would like to answer this question. Does Class C fly ash won't be effective?
You want to use the fly ash that has no benefits. If you are using the fly ash for beneficial use for other purposes, we want to use something that nobody wants it, right?
Yes.
So that's the advantage of what we want going after. So you have a lot of demand to use in concrete and other things.
Yes,
fly ash that is not useful there, then you want to use them here.
Thank you, sir. So now I'll request Dr. Survi. Yes, please unmute yourself.
I want to thank you, Professor Reddy sir, for this wonderful lecture, for this information on utilization of fly ash in liner system. Though in India, we didn't start much using the liner system. Someday when we start using, we will absolutely take care to utilize this fly ash for this. Thank you, sir.
Thank you so much.